Happy to have you again. This time talk about zkSNARKs in the random oracle model with unconditional UC-Security. Go ahead.
Thank you. I'm good there. I don't have to wait anything.
They just gave me the green light.
Perfect. Awesome. Okay, so hi everyone. So good to see you again. So I'm here to present zkSNARKs in the ROM with unconditional UC-Security. And this is joint work with Alessandro Chiesa. And the one takeaway that you should take out of this work is that constructions of SNARKs from IOPs are already UC secure with no additional modifications. So if you are using something which is a Stark base or Fry base, you probably already have a UC secure SNARKs, you just didn't know it yet. So let me give you some motivation on why you should care about UC security. So first of all, we've seen zkSNARKs a lot this talk, so I think I can skip this part. But my first claim is that SNARKs are kind of like moved past this academic like area in which they're like confined in labs, and now they're starting seeing a lot of real-world adoption, like the previous talks have made abundantly clear. And I'm giving here just one example of one way in which these zkSNARKs are used. So improve base rollups to improve scalability of blockchain. So roughly, you have a blockchain, you have a throughput problem. So what you end up wanting to do is trying to delegate some computation and use SNARKs to ensure validity. So what you will have users of the rollup, which then submit transaction to a service operator. The service operator will collate this transaction into a single proof and update the state function accordingly. The proof and the updated state function will then be posted on the blockchain, and then the validators can check the validity of the proof. And since like the cost of like checking this proof is much less than actually performing the update operation themselves, there's a gain in the network, and you can increase the throughput. So is this important? We're gonna get back to this slide anywhere during the talk? Not at all. So the only thing I wanted to make is that we would like to. This is a complex system, and we would like to have modular security analysis. Our goal would be to say, like, look, if our SNARK is secure and other components of the system are secure, then the whole system is secure. And in cryptography, there's one tool which was very aptly named for this particular thing, which is the Universal Composability Framework. So in our focus in this talk is giving tool to talk about security of this first component of this recipe, so the proof system, and show so that when you're conducting a holistic security analysis of a larger system, you can use that to conclude security of the overall system. And so the natural question that this leads to is which zkSNARKs are UC secure? And let me just give you a little bit of what was known before this paper. There's first a line of work which I affectionately call the COCO line of work because it was the original one that introduced it, which essentially the way that they achieve UC security is by appending an encryption to the witness to the proof. Why do they do this? Well, the UC security framework, as we will see later on, requires some stringent properties. So, for example, the extractor that you require has to be straight line and black box. So a large number of SNARKs in the literature do not satisfy this property. So what you need to do is you need to help the structure in some way. So what these lines of work did, what they append an encryption of the witness to the proof, and that is so that the extractor can then look at the proof, decrypt, and then extract the witness. So this is how you achieve straight line. But since the encryption of something must be at least as large as the thing that you're encrypting, you lose succinctness in this case. There's other works that looks on universally composable Sigma protocol, and roughly they take a Sigma protocol, they compiling with using a variant of the Fish-Lin transform, but again the starting protocols are not succinct, and the compilation step is expensive because roughly you have to do, you're not just doing a Fiat-Shamir transform to convert these Sigma protocols into an argument, but you're doing a Fish-Lin transform. So what we would like to do is improve on this. So this is all the previous non-succinct UC secure SNARKs. Recently there's been another work which has been able to achieve succinct universally composable SNARKs. these witness succinct universally composable SNARKs. And roughly, the idea is something which is similar to the previous work I was talking on Sigma protocols. So you're also doing some Fischlin-like techniques. So the first thing to notice is the first UC-secured SNARK, so where you actually have full succintness. And they contract them by combining a simulation extractable SNARKs in the standard model with a polynomial commitment scheme. Roughly what you do, you use Fischlin-like technique to force the prover to rewind itself, so you can actually design a straight line extractor. So as a prod, you get succinct proofs. You are UC secure in the non-programmable observable global random oracle, which is a mouthful. But the construction does not really reflect like the way that SNARKs are deployed in practice. It's expensive because you have to do a lot of Fischlin, and for each Fischlin iteration, you have to provide a polynomial evaluation proof. And also, it focuses on asymptotic security. Since the scheme is not practical, they don't really care about the concrete security, which is something that instead practitioner might be more interested on. So, what do we aim to achieve and what we achieved in these works? So, the main goal is to show that existing zkSNARKs are UC secure. In particular, we want to have something general enough to include deployed SNARKs. We want to achieve succinctness, so we want to achieve the full notion of succinctness, so nothing of the circuit succinct, just witness succinct, proper succinct. And we want to do things without cryptography, so we want to stay in the pure random oracle model. It has got a number of benefits. In particular, our SNARKs are transparent, they're plausibly post-quantum secure, and you can get unconditional security in the random oracle model, so with no need of computational assumptions. Further, during the work, we took a painstaking amount of time to work out the concrete security bounds of our constructions. So this should enable people to inform their parameter settings for deployments of this complex system, which I think should be helpful for people. Okay, so let me start with giving you some background on UC and all this kind of stuff. But are there any questions so far before I dive in? Okay, cool. Then let's have a bit of background. And the first thing that we need to talk about is the UC security. So the motivation, as I said before, is to conduct modular security analysis of protocol. And why did we choose, there are other frameworks, why did we choose UC? Well, UC by now is battle tested, is a gold standard. People have been using it for more than 20 years now. There's a very vast literature, so contributing it to it we think is worthwhile. The crown jewel of UC security is the composition theorem, which roughly states the following. So if you have a protocol, an ideal functionality, and a calling protocol, if the protocol satisfies a property which is called UC emulation, so if the protocol UC emulates this ideal functionality, then whenever I have a protocol which uses the previous protocol as a subprotocol, I can replace it I can replace the subprotocol with the ideal functionality. And the two resulting larger protocols will UC emulate each other. So roughly that means what that means is that you can really replace the building block that you're using with something which satisfies some ideal properties. And an adversary will not be able to tell the difference. And this is what enables us to conduct this modular analysis of things. What is this notion of UC emulation? So I've helpfully put a lot of variables on the top right. So we say that a protocol UC emulates some ideal functionality, and the goal is that you don't want an adversary, which in the UC setting is called an environment, should not be able to tell apart the protocol from the ideal functionality. And the definition that we have is that basically for every adversary, there exists a simulator such that for every environment, something holds. And this is what something holds is that the difference between a real and ideal game should be small. In particular, let me just point some attention on the order of quantifiers here. So the real adversary that we're playing against in the UC security game is the environment. And you can see that the environment is quantified after the simulator. So the simulator in particular cannot depend on the environment. And this is what this change of quantifier is what actually we will what imposes the requirement that the structure that we have are straight line and black box, which kind of like creates the whole issue of trying to achieve UC-secure SNARKs. So what are the two games? So in the real game, you will have an execution of the protocol, which might have various parties, while in the ideal games, they will have an ideal functionality, and there will be some dummy party which just forwards everything to this ideal functionality, which you can think of all the other trusted party. In both games, the environment will interact with the protocol. It can pass input to it. And further, there will be, in the real game, there will be an adversary, which is able to write information to what are called the backdoor tapes of these parties in the protocol. You can think of these as like sending messages like to corrupt parties or that. In the ideal game, the adversary is instead simulated by the simulator, which then talks to the ideal functionality. And these two security games should be indistinguishable, where indistinguishability is over the final bit output by the environment. So if we're able to show that in these two games are equal, then we are basically fine. So, okay, now, I talked a bit about UC. Now we need to talk about the other object of our investigation, the random oracle model. And the one that we looked at in the UC setting is a bit different from the normal one you're used to, because it needs to be shared by every functionality. And there's some work on this, and the model that we chose is the global random oracle model. And roughly the goal is to get a ROM-like interface that every party in the security experiment can have access to. And the flavor that we choose, because in this in the global random oracle literature there are a bunch of flavor, is the restricted, programmable, and observable global random oracle, which is a mouthful again. So roughly, what does this random oracle allow you to do? So it allows you to query it, like any good random oracle should allow you to. It allows you to observe. So if you have there is an observe interface that you're able to get to give you the queries of illegitimate adversaries, such as example the environment. This in particular is what we will require for abstraction, for be able to use the straight line extractor of the SNARK we construct. We will need some programmability notion, because we will require that the simulator is able to actually program the global random oracle while maintaining some consistency, of course. But this is a global thing that everybody can use, so we actually need to somehow, because now, for example, the environment or the adversary could be able to program the random oracle as well, and we do not want to allow that to forge proofs. So in particular, the global random oracle has an additional check, which is the is programmed, which essentially allows only the simulator to be able to program undetectably, while all other honest parties will be able to detect if a query has been programmed. And this is the advantage that the global random oracle affords the simulator compared to other parts in the experiments. And in particular, this is something that we really need to achieve zero knowledge. In the same way in which when you're doing zero knowledge in the ROM, you actually need to have some undetectable programmability. So, global random oracle. Questions on this so far? Cool. It's a random oracle, but it's global. Okay, now, oh, sorry.
I don't know if it's a Bluetooth.
I think it's on. SID is a simulator ID.
Sorry?
SID is a simulator ID.
Session ID.
Session ID.
We domain separated various sessions of the protocols. Good question.
Other question? Go ahead, sorry.
Awesome. So okay, now we can talk about the functionality that you want to emulate. Roughly, you just want to figure out what would be the ideal SNARK that you would like to have, and the one that the ideal functionality that we use is one which is borrowed from the previous work of Lishansky and Rosenblum. So, to model zero knowledge, we will have that the prover generates a proof using a simulator, which makes no use of the witness. And the verifier, when it accepts a proof, it will also aim to extract a witness, and it will fail noticeably if it doesn't manage to. We also model completeness in that proofs which are generated by the proof interface are always accepted by the verification interface. So writing this in code, this is roughly what it looks like. So as I said before, The proof interface uses a simulator to generate proofs, and the verification aims to extract. In particular, we also make use of the is-program check, so we don't accept any proof which makes use of points which were not programmed by the simulator. So for example, if the adversary starts the programming functionality to like generate a proof, then when I verify, I don't count that as a valid proof. Sorry. Yeah. So
repeat the question.
Yes. So the question was, what is this EaseGRO? What does it succeed when it does not succeed when he? Yeah. So EaseGRO is a structure. So he will run from the query list obtained from the global random oracle. So this is the traces of the queries of the adversary to the random oracle, and will aim to extract a witness from the proof. It will succeed if the extracted W is a valid witness for the relation, or otherwise, if it's not, it will fail. And this fail, you can think it just outputs some some noticeable failure symbol.
So pi was generated here without looking at the witness. So how can he possibly, from a such a pi?
I don't know if I can show. So if pi was generated by the proof thing, we just accept. Because the ideal functionality knows which proofs are generated by itself.
Okay, thank you.
Yep. Awesome. So the protocol that we consider is a very simple wrapper protocol. So we take any argument in the ROM, and then we turn it into a protocol in the GROM. And how do you do it? Well, it's really simple. You just, in the setup, you do nothing. In the proof, you run the prover by querying the random oracle accordingly. And in the verifier, you run the verifier by querying the random oracle accordingly and rejecting if any of the things were programmed. So this is our wrapper protocol. It's very lightweight. Now, I hope I haven't lost you so far, but now our goal will be to find some argument in the random oracle model such that when you wrap it in this protocol, you will UC-emulate the argument ideal functionality in the global random oracle model. So this is what we will aim to do. Cool questions on the approach so far? Okay, so what's our result? So our main theorem is that there exists a zkSNARK which is unconditionally UC-secure in the global random oracle model. Further, we put forth some notion of UC-friendliness for arguments. So if the argument system satisfies these UC-friendly properties in the ROM, so just in the pure random oracle model, then the corresponding argument will yield a UC-secure protocol in the global random oracle model. So you can lift security in the ROM to security in the global random oracle if you satisfy these stronger UC-friendly properties. Moreover, we show that classical construction of zkSNARKs, in particular the Micali and BCS constructions, satisfy these UC-friendly properties. So focusing on Micali for now, we show that if the PCP in Micali is honest verifier, zero-knowledge, and knowledge sound, then the Micali construction is UC-friendly. And note that in particular, these are exactly the same properties that you need to achieve zero-knowledge and knowledge soundness for Micali in the ROM. So you don't need to pay anything more in order to achieve UC-friendliness and consequently UC-security. For BCS, the situation is exactly the same. The notions to get a zero-knowledge and knowledge sound argument in the ROM from BCS is honest verifier zero-knowledge and state restoration knowledge sound. Those same exact conditions suffice to give you a UC-friendly argument and consequently a UC-secure protocol from BCS. So it essentially means that to get UC security from BCS, which underlies a lot of very deployed practical protocols, you don't need anything more than what you were already paying for. So yeah, this is our main result. Now I can dive into techniques. Also, I don't know how much time I have, so feel free to wave if.
Pick the favorite technique and go for it.
Okay, cool. Yeah, so okay, maybe I'll skip. So we did some work on. So this is some modeling things or modeling share functionalities, which is important, but I will not go into it. We put forward. So in UC-Security, usually you just deal with computationally bounded adversaries. So in our case, we want to aim for unconditional security, so we had to tweak UC a little bit. So we introduced this UC with budget model, which roughly allocates a budget for whatever the adversary is able to do. And the budget can then be spent on queries to different parts of the securities game. In particular, there's a query budget, a programming budget, a proving budget, and a verification budget. And then we use these budgets to provide concrete security bounds. So that was pretty cool, and we hope that people use it later on. So, okay, our main lemma, this is what I will focus on, is that if you have an argument in the ROM with these three properties, which I call UC-friendly properties, then you end up getting a UC-secured zkSNARK. Note that these properties really relate to the same, to the corresponding properties in of completeness, zero knowledge, and knowledge soundness. And the way that the proof essentially goes is really by an hybrid argument, and it's actually a very simple proof because these properties are defined exactly to make this game hopping work. So, you're doing this game hop. In the first game hop relies on the fact that this simulator has this extra power to program undetectably. Then you do a hop via UC-friendly completeness, one via UC-friendly zero knowledge, and then one via UC-friendly knowledge soundness. So it's a very nice and modular proof. And maybe I'll say a little bit on why we chose the Micali construction as what we were interested in first considering it. And first, it is the canonical construction of a zkSNARK in the pure random oracle model. Second, we know that Micali has got a straight line black box extractor, which makes it compatible with UC. So we know there's hope in actually getting something that can work with the UC framework. Proofs, they are built by constructing miracle trees, which are inherently, they satisfy some good non-malleability properties. Like knowledge soundness for UC also implies simulation extractability. So starting from a proof system which has already got this strong non-malleability and no homomorphism properties seem very natural. And finally, if you understand Micali, you basically understood BCS. So you can go and you can really reach our target of getting security for deployed zkSNARKs. So I'm gonna skip of what the Micali is because Ali did a good job about it on the first day, even though there are a lot of slides. And I'm just gonna give you some flavor of what one of these properties is, and then I'll conclude. So UC-friendly completeness is the property that an adversary should not be able to make honestly generated proof fail to verify. And intuitively you might think like, but this is, why doesn't perfect completeness like suffice? And that is because you have now this programming of the random oracle by the adversary, which can create troubles. So in particular, the property states that an adversary which has access to a query and a programming oracle, and a proof oracle which generates proof using the honest prover, is not able to output an instance proof pair that was previously queried to this oracle, on which the verification either the verification rejects or the verifier queries program point. So we want that this probability is small. And the reason why this is important is because in the UC game we reject any proof that contains program point. So we want to make sure that an adversary is not able to deny accepting proofs. So this is all our properties, like we will see later on, they kind of have this similar flavor. They're an extension of like known properties, but which have some programming involved now. And I'm not gonna go too much into the detail. We can talk about it later, or you can read the paper. But I'm gonna just go to the conclusion, because yes. So the conclusion, the selling point is Micali and BCS are UC secure in the global random oracle. No extra modification needed. You don't have to pay any more than what you were already paying. And further, we have some very beautiful theorems with very nice concrete security bounds, which were painstakingly worked out. So you can now use it to inform your decision of the security parameters of your SNARKs to make sure that your system is UC secure. So I think thank you for your attention, and I'm open to any questions, comments, or.
Okay, I have one question. So you presented this for the conference for ZKProof. Do you also present this in a written paper that peer reviews so that it can be referenced and used later on?
Yes, it's in the first slide is 2024-724 on ePrint, I think.
And do you have like a target like conference and?
I don't want to give away the name of the game.
Okay. No problem. But people could start using those results now.
Yes, of course, you know, people should not like rush into using these things. There needs to be the peer review process. Like it's a long paper. There's a lot of results. We are confident in things old, but yes, we hope that this leads to people using it in practice. But you know, of course, papers have bugs. This is a long paper. You know, there's a constant probability each page has a bug. So, like you can you know, wait a little bit. But I think the results should be sound. I really hope so.
Okay. Any more questions? Okay. Thank you very much.
Thank you.